Hyperloop, your future commute. To drive from LA to San Francisco takes approximately 5 hours and 32 minutes and costs around $100. To fly the same distance takes 1 hour and 21 minutes and costs $150 round trip. Taking a boat or a train would cost less but would take much more time. What if you could make the trip in 35 minutes for $40 round trip? For years, the world has relied on 4 basic modes of transportation, but what if there was a 5th mode? A type of transportation that costs less than current modes while still being safer, faster, and more convenient, all while being completely powered by sustainable energy. Introducing the Hyperloop. It is a conceptual high-speed transportation system put forward by famous entrepreneur Elon Musk. The idea incorporates tubes in which capsules ride on a cushion of air and are driven by a combination of magnets and air compressors. Let's talk more about each component of the Hyperloop. Steel tubes that measure 7 feet 4 inches in diameter will be welded together in a side-by-side configuration to allow the capsules to travel both directions. Pylons are placed every 100 feet to support the tubes. The tube is specifically sized to provide optimal airflow around a capsule, improving performance and energy consumption at the expected travel speed. Sealed capsules that can carry 28 passengers each will travel along the interior of the tube. The capsules depart from the station every 2 minutes under normal demand and every 30 seconds during peak usage hours. The capsules are separated within the tube by approximately 23 miles during operation. The capsules are supported via air bearings that operate using a compressed air reservoir and aerodynamic lift. Magnets, or stators, are mounted along the length of the tube at various locations and work with the rotors that are attached directly to the capsule to accelerate and slow down the capsules as needed. For travel at high speeds, the greatest power requirement is normally to overcome air resistance. Aerodynamic drag increases with the square of speed, and thus the power requirement increases with the cube of speed. For example, to travel twice as fast in a vehicle, the vehicle must overcome 4 times the aerodynamic resistance and input 8 times the power. Just as aircraft climb to high altitudes to travel through less dense air, the Hyperloop encloses the capsule in a reduced pressure tube. The air pressure inside the tube is about 1/6 the pressure of the atmosphere on Mars. This means the drag force is reduced by 1,000 times relative to drag at sea level conditions, and would be equivalent to flying at an altitude over 150,000 feet. In addition, the capsule features streamlined aerodynamics and an air compressor to further reduce air resistance. The compressor serves 2 purposes. First, without the compressor, there would be a large buildup of air mass in front of the capsule, which would greatly increase drag. The compressor allows the capsule to travel in the narrow tube without choking the airflow that travels between the capsule and the tube walls by compressing the air and then sending it through the back of the capsule. Secondarily, the compressor also supplies air to the air bearings that support the weight of the capsule inside the tube throughout the journey. The Hyperloop travel journey will feel very smooth since the capsule will be guided directly on the inner surface of the tube via the use of air bearings and suspension. Suspending the capsule within the tube presents a substantial technical challenge due to the transonic cruising velocities. A conventional wheel and axle system becomes impractical at high speed due to frictional losses and dynamic instability. A viable technical solution is magnetic levitation. However, the cost associated with the materials and construction is prohibitive. An alternative to these conventional options is an air-bearing suspension. Air bearings offer stability and extremely low drag at a feasible cost by exploiting the ambient atmosphere inside the tube. Put simply, imagine the capsule floating inside of the tube like a puck on an air hockey table. Hyperloop stations are intended to be minimalist but practical, with a boarding process and layout much simpler than airports. Due to the short travel time and frequent departures, it is envisioned that there will be a continual flow of passengers through each Hyperloop station, in contrast to the pull situation at airports, which lead to lines and delays. Safety and security are paramount, and so security checks will be made in a similar fashion as the TSA does for the airport. The process could be greatly streamlined to reduce wait time, and maintain more continuous passenger flow. The stations are isolated from the main tubes as much as possible in order to limit air leaks into the system. The major stations for Hyperloop are suggested based off high traffic regions between major cities. The largest cities in California, such as Los Angeles, San Francisco, San Diego, Sacramento, and Fresno, are being considered for station locations. One additional traffic corridor that will be considered early on will be between Los Angeles and Las Vegas. By placing solar panels on top of the tubes, the Hyperloop can generate far in excess the energy needed to operate. This takes into account storing enough energy in battery packs to operate at night and for periods of extended cloudy weather. The design of the Hyperloop has been considered from the start with safety in mind. Unlike other modes of transportation, the Hyperloop is the single system that incorporates the vehicle, the propulsion system, energy management, timing, and route. Capsules travel in a careful environment, making the system immune to wind, ice, fog, and rain. The propulsion system is integrated into the tube and can only accelerate the capsule to speeds that are safe in each section. With human control error and unpredictable weather removed from the system, very few safety concerns remain. All capsules would have direct radio contact with station operators in case of emergencies, allowing passengers to report any incident. In addition, all capsules would be fitted with first aid equipment. The Hyperloop allows people to travel from San Francisco to Los Angeles in 30 minutes. Therefore, in case of an emergency, it is likely that the best course of action would be for the capsule to communicate the situation to the station operator, and then for the capsule to finish the journey in a few minutes where emergency services would be waiting to assist. The vast majority of Hyperloop travel distance is spent coasting, and so the capsule does not require continuous power to travel. The capsule life support systems will be powered by 2 or more redundant lithium-ion battery packs, making it unaffected by a power outage. In the event of a power outage occurring after a capsule had been launched, all linear accelerators would be equipped with enough energy storage to bring all capsules currently in the Hyperloop tube safely to a stop at their destination. In addition, linear accelerators using the same storage would complete the acceleration of all capsules currently in the tube. For additional redundancy, all Hyperloop capsules would be fitted with a mechanical braking system to bring capsules safely to a stop if needed. Hyperloop capsules will be designed to the high safety standards and manufactured with extensive quality checks to ensure their integrity. In the event of a minor leak, the onboard environmental control system would maintain capsule pressure using the reserve air carried on board for the short period of time it would take to reach the destination. In the case of a more significant depressurization, oxygen masks would be deployed just like airplanes. Once the capsule reached the destination safely, it would be removed from service. A capsule becoming stranded in the Hyperloop tube is highly unlikely as the capsule coasts the majority of the distance at a high speed, and so there is no propulsion required for more than 90% of the journey. If a capsule were somehow to become stranded, capsules ahead would continue their journey while capsules behind would be instructed to stop. Once all capsules behind the stranded capsule have been safely brought to rest, capsules would drive themselves to safety using small onboard electric motors to power deployed wheels. All capsules would be equipped with a reserve air supply great enough to ensure the safety of all passengers for a worst case. California is no stranger to earthquakes, and transport systems are all built with earthquakes in mind. Hyperloop would be no different, with the entire tube length built with the necessary flexibility to withstand the earthquake motions while maintaining the hypertube alignment. Each pylon will be equipped with 2 adjustable lateral dampers and 1 vertical damper. These would absorb the small length changes between pylons due to thermal changes, as well as long-form subtle height changes. As land slowly settles into a new position over time, the damper neutral position can be adjusted accordingly, allowing for continual adjustment. Hyperloop would feature the same high level of security used at airports. However, the regular departure of Hyperloop capsules would result in a steadier and faster flow of passengers through security screening compared to airports. Compared to planes and trains, each capsule contains a smaller amount of passengers, meaning that they would less likely be targets. Also, the capsules are not drivable and therefore could not be used as a weapon like a plane can. As we see here, the total cost of the hyperloop is estimated to be under $6 billion for 2 one-way tubes and 40 capsules to carry passengers. The current high-speed rail in California is estimated to cost $68.4 billion for a train that averages 164 miles per hour. Even if the hyperloop quadrupled its estimated budget to $24 billion, it would still cost less than half of the proposed high-speed rail. Given the route, the design, and the logistics, the hyperloop can transport 7.4 million people per tube each year. Amortizing the construction costs of $6 billion over 20 years, and then adding the daily operational cost, it comes out to be $20 per one-way ticket on the hyperloop. As stated before, the life of the hyperloop would be 100 years. This means the first 20 years would cover the cost of building it, with the last 80 covering daily operational costs and repairs. Until recently, the hyperloop idea has been mostly a theory, but recently there has been more fuel added to the hyperloop fire. On January 15th of this year, Elon Musk tweeted that they will be building a hyperloop test track for companies and student teams to test out their capsule designs. This will most likely be built in Texas. Then, in February of this year, it was announced that a group called Hyperloop Technologies has stepped up as the first funded Hyperloop startup company, armed with $8.5 million of pool money and plans for another $80 million funding round later this year. The Hyperloop Technologies has hired a dream team. They have enlisted a formidable lineup of Silicon Valley and Washington superstars, most who have a strong connection with Musk. This company has several groups currently working for them. They have a group of math students at Harvard building a fairly advanced route optimization model that plans the cheapest and least nauseating path to link any city pair. They have an electric motor company in Portland working on the capsule's propulsion system. They also have a team of UCLA architecture students who have created scale models of passenger interiors out of wood. While the idea is still an estimated 10 years out, Hyperloop is picking up a lot of steam. Hyperloop Technologies has stated that there is no turning back now, and there is plenty of financial and political backing to take the Hyperloop from a dream to the fifth mode of transportation.